1. The time step, and we write here hn because it can vary. So what we have used here just before was that this distance here is then the chosen time step for going from time level n to n plus 1, and this difference here is the hn times the slope. And the slope, we write it first, the y prime of tn, and that can then be expressed as the hn, the time step, times the right-hand side of the ODE at tn yn, because we know tn, the time level, and we know the approximate solution there. So then we simply get from that Euler's method is then that we just saw before, yn plus 1, the solution at the new time level is equal to the solution at the old time level, and then we add simply this hn times f of tn yn. So that is a way we can illustrate that directly, but we can also obtain this solution for Euler's method by Taylor expansion. So 2 can be obtained by Taylor expansion. And then we can write y at t plus h. So t is now our tn and h is our hn. Then we do a Taylor expansion in a similar way as we did it before with the central difference. There we used the Taylor expansion of u of x plus h. Now we use a Taylor expansion of y of t plus h around t. So then we get our solution at t plus the time step h times y prime of t plus h squared half times the y double prime of t plus higher order terms. And if we stop just after the first here, at the first h, then we can, that is what we use then for the method, using that y prime by the ODE is equal to f of ty. Then we can identify this here as the local truncation error. That is the local truncation error. And we shall give it a name. We shall call it epsilon. And this is related to the new time level, that therefore it will be called epsilon n plus 1. And this Taylor expansion that we have done here, that we have done for t equal to tn, for y, for h equal to hn, and for y prime of tn is equal, let's see, yeah, is equal to the f of tn yn. So that is what we have been using, and then we get Euler's method that we have here. When we do this, then we just stop after the first order and we drop the second order and the higher order. So we do Taylor expansion for this, and we can and dropping the O of h squared term, that is this term here, and higher order terms. So that is another way to derive Euler's method. Now, if we look at this local truncation error, we see that it is of second order because we have here an h squared. So then the Taylor expansion and the term that we drop shows then that this drop term, which is the local truncation error, E n plus 1 is of second order. Now we want to give the definition of this. We have already seen it here, but we want to give it really a proper definition. And that is then 4, and we do it now for the time level n. That is then the numerical solution that we compute, in our case with Euler's method, minus, and here comes now a little bit something that I have to explain. That is now the exact solution to the ODE with a certain property. It looks a little bit strange, but I'll tell it directly what it means. This un minus 1 of t is the exact solution of the ODE that we want to solve. That was ODE 1. It is 1a, but now with a special initial condition, namely that the initial condition now is at the previous time level n minus 1, the numerical solution that we have there, un minus 1. That is similar to what we are doing here. Here, so what we have here, that would be the exact solution, but starting from the time level n with the numerical solution there. So that is what we get. That would be our, the value here would be our y n plus 1, but our exact solution starting from here, that would be here. So that would, in this notation, here we would be at un, and then that would be then tn plus 1. So this difference, un plus 1 minus this, that would be, in that case, the local truncation error. So that would be, in our case, it would be the en plus 1. Of course, we have the definition there for n, but here we have the illustration is for n plus 1. So, but that is not the error. This is not the error, it is just the local truncation error. That is the error that we do in going from one step to the next locally. The error that we do is the comparison with the exact solution starting with the initial condition at t0, not at the previous time. therefore we can define now the error that we are later on really interested in, that is the global error. And that is defined by Tn is equal to the numerical solution minus the exact solution at Tn. So numerical solution minus exact solution. And that is the global error of a numerical ODE method. Now we continue that. That can be estimated so we can give some upper bound, and that is the following: 5. The absolute value of the global error is smaller or equal to some constant c times the sum of all the local truncation errors. So we have defined here, and they we can control by doing Taylor expansion, as we saw. But now we have this, which allows us to estimate the global error. And where the C, that is not so important, but in the literature, that was in the book by Hayvan-Nosset-Vanna, you can find that this can be done by some constant, exponential of some constant L times Tn minus T0 divided by this constant L with the, this is now some new notation, it gets a little bit mathematical, but don't worry. That is the right hand side of the ODE f. If that is a vector, we can take the derivative with respect to y, and we get the Jacobian matrix. So this is a matrix, and this is the spectral radius. Spectral radius, that is the maximum of the lambda, and the lambdas are the eigenvalues of this matrix. Lambda eigenvalues of the Jacobian matrix f with t, y, dy. And that should be smaller or equal than this constant L. This is technical, so the only thing that we need to know is this is a constant. For our considerations, the C is just a constant. As you see, it depends on the right-hand side of the ODE f and the eigenvalue of its Jacobian. They must have some bound, L, and it depends on the time difference from the initial condition to the time instant Tn. That's all. So for the consideration, we only need for this C is a constant. So now we can try to estimate the this global error, capital En, by estimating the local truncation error. Now I want to make it a little bit more general than just discussing the explicit Euler method, by assuming now that the local truncation error is of order h to the power p plus 1. In our case that we are discussing, p is 1 for Euler's method. But we can make it more general. Then we can estimate the right-hand side here of this estimate, C times the sum from 1 to n of the local truncation errors, L, by some constant, C, that we have given here, times the sum, L from 1 to n. Now these EL in itself, they can also be estimated by some constants times power h to p plus 1. So we have then here some constants, KL, h to the power p plus 1. And then we simply take, say, the maximum of that. The maximum of all these constants KL, or usually it's some function, so we can take the maximum then of the function describing these k's. And then we have then the sum of the h, so then we have L from 1 to n, h to the power p plus 1. So the L does not appear, so we have this sum n times. So that means we get here an n times h to the power p plus 1. And now we need to know that n is the number of time levels. If we assume we have a constant time, step h, if we are not, then we can always get an average. Then we can determine the h, say we call that now the average h. We can determine that as the Tn minus the T0, that is our time interval, divided by n, right? So that is what Radar the other day explained as T max divided by n to get then the time step delta t. From that, we can see that n we can express as Tn minus T0 divided by h. So then we can introduce that here. So therefore, we get from that this right-hand side is then some new constant here, saying that let's call that say ck something. And then we get here the n, that is then the Tn minus T0 divided by h. What we discussed here is the n, times h to the power p plus 1. You see, h takes away one of the h here. So that means we get then here some new constant. And the important thing is that we get here h to the power p. So that means that we can estimate the global error by this expression, which is of the order p. So the conclusion of that is that the En, the global error, is of order h to the power p. If the local truncation error is, that was the assumption, of order p plus 1. So when going from the local truncation error to the global error, we lose one order. We can imagine that by summing up these local truncation errors, we do it n times, and as we see here, that is proportional to 1 over h. So then we can say, regarding to Euler's method, for which we had p equal 1, that the global error for Euler's method is of first order. Euler's method then is first order. That means when we do a grid refinement, we compute to a certain n time t max, we get some error. If we do it with h half, we get an error which is then h to the power 2 proportional to that, so it's essentially the error that we had at h halved. If we had a second order method, it would be as we had for the central difference method, it would be the error for h divided by 4. So the error then goes down very slowly for first order method. So that is the important conclusion from this analysis, that if the local truncation error is of order h to the power p plus 1, then the global error is of order p. So that is that. If local truncation error En is of order h to the power p plus 1, then the global error En is of order h to the power p. We have here these three different ones. And that is something that is uniformly valid for ODE methods. And as I just said before, the global error of Euler's method is first order. And that means that Pn, the global error, is order h for okay. So then that. So now I would like to give you a little animation of these different concepts of local truncation error and global error for a very simple example. So we have here the example of the ODE y prime is minus 5y. The initial condition at t0 equal to 0 is 10. What we see here, so we start here from 10, and we have a time step of 0.1. So here we have them, and this is now this, what we see here is the numerical solution with Euler's method. So we have here 2, 3, 4, 5 time steps. So we get them to time 0.5. This is the exact solution. We can write that immediately. It is 10 times e to the minus 5t. That is the exact solution. We see then, can then identify at each time level, we can identify the global error. So here we have the global errors at each time. That is the difference between the numerical solution and the exact solution, where we have started with the same initial condition as we have started the Euler method with. For example, if we go to the final time, then this would be the y5, the numerical approximation at time 0.5, it is here, but the exact solution to the ODE would be here. So this difference here is the global error at time level 5 in our case, because we have 5 time step up to here. So that is that. Now this is the solution, by the way, so the t and the computed approximation given by Euler's method at these time instants. Now we want to also to illustrate the local truncation error that we need to compute things. Let's see. The right one? I have to start it. Now it's starting. Okay. So we have the same thing as before, the numerical solution by Euler's method. The exact solution starting with the same initial condition as we computed. But now we want to visualize also the local truncation error. In the local truncation error, if we start here, then we do Euler's method going from this point to this point. Then the exact solution of the ODE starting from the previous numerical solution, which is the initial condition here, would be here. So the difference between the numerical solution and the solution starting from the previous time level is, in that case, the local truncation error equal to the global error for the first step. But here we see a difference for the second one. In the second one, the y2, Euler's method computes this, starts here, it takes the slope from there as straight and gets here. So this is the y2. But the numerical solution, the exact solution, when we start here with this solution here, is here. So that is the exact solution to the ODE with the initial condition at the previous time level, which is in that case t1, with the numerical solution y1. So then we would get this green solution. And the difference between that is the local truncation error. Again here, the same thing. Euler's method goes from y2 to y3. But if we would start from here, from t2, with y2 as initial condition, the exact solution would be the green one we'd get here. And the difference here, again, is the local truncation error. So then you can imagine when we sum up these 5, that we get some upper bound, in this case, you can see it, of the global error here. Because that is the global error, the difference between the numerical solution that we have on the red line here and the blue line that ends here is the exact solution there, with this initial condition, with 10. So that is usually what we are interested in, global error. But we use these local truncation errors to estimate the global error. And that is the solution then for Euler's method. So when we do the analysis, we analyze the local truncation error and use what we saw before, that the global error is 1 order lower. Local truncation error is second order, the global error is first order. Okay, so that gives you an idea of the local truncation error and the global error. Now we have seen the derivation just by the graphical interpretation in the start, then using Taylor expansion. Another way to derive Euler's method is by using the forward difference approximation that we discussed just last time. So, Euler's method, let's get a little bit up. Euler's method can also be derived by approximating y prime, that is the first time derivative at the time level Tn, in the ODE 1 by the forward difference. Forward difference approximation. And that would give us the following. We would then take the yn plus 1 minus the yn and divide by, now let me use another notation here, which is equivalent, that is the time step, delta t. And on the right hand side we would then have the function f at this time level n, that is then the Tn, and we would have the numerical solution there, Yn. So when you talk about forward and backward difference, it is important that you always say, where are we and where is the right hand side? So here we go from n to n plus 1, but the right hand side is then at n. Of course we'll also see later on the backward difference, where we start from n plus 1. But this is then equivalent to Euler's method. And these notation, delta t or h, that is used, either one is used, so they're meaning the same thing here. So what we have here, just to write it, is equivalent to having un plus 1 equal to, we multiply simply by delta t and bring the yn on the right hand side. Then we have exactly the form that we derived earlier of Euler's method. It is just that we have used here delta t for h, otherwise it doesn't see. So there are different ways to derive the method. Now let us see if we can derive higher order methods, and you have seen that in your numeric course, I hope. And one way to do that is by using Truncation methods. They go back to the mathematicians Müller and Kutter, and they derived these methods a little more than 100 years ago. And I think in 2004 there was the 100th anniversary of the classical Runge-Kutta method. That was celebrated by mathematical conference.